Hi, in this video I'll teach you what is the fundamental theorem of invertible matrices, and we will prove the theorem. The theorem gives you different statements which are equivalent for a matrix, a square matrix, to be an invertible matrix. Okay, let us just write down what is the theorem, the fundamental theorem. First of all, it assumes that we have a matrix which is a square n by n matrix. Then the following statements are equivalent. It means that whenever you see one of these guys, then you can conclude the other ones are true also. So first thing is A is invertible. This is what we have been working on. Then the second version is that, well, AX equal to B, the linear system, AX equal to B, has a unique solution for all vectors B in Rn. And the third one says that, well, the homogeneous system AX equal to 0 has only the trivial solution. And the fourth one says that, well, the reduced row echelon form of A is the identity matrix. And the fifth one says that A is the product of elementary matrices. First of all, you notice that the nature of each statement is different, and that's why it is important for us. And the way we will prove it, we go from first one to second one. We show that the second one implies the third one implies the fifth one, the fourth one, and the fourth one implies the fifth one. And then we can conclude the first one from the fifth one. Okay, so let's just do the proof for this one. It will be very quick one because, okay, so we are assuming one and we want to prove two. So A is invertible. This is the assumption. Then when you have AX equal to B, you can multiply both sides by A inverse. So we will get A inverse AX equals to A inverse B. These two will give you identity. Identity X is equal to A inverse B, and that means that X is equal to A inverse B. That is the unique solution we have been looking for, yes? How about second one implies the third one? Well, this is obvious. Yeah, why? Because just let B to be equal to 0 vector. The second statement says that for all B, such a thing has unique solution. Now, in particular, the statement 2 is true for B equal to 0. So that means that AX equal to 0 has a unique solution. But we know that AX equal to 0 is homogeneous system. So already X equal to 0 is dot a solution. So since it has a unique solution, so that is going to be the only solution of the system. How about a third one implying the fourth one? Well, if you have ax equal to 0 has unique solution, you can start Gauss-Jordan elimination method. Yes. And you row reduce it to row reduce row echelon form. If you do that, to have unique solution, it means that every column needs to have one leading one. So this one is going to have one leading one and so on. But this matrix is n by n. So it has n leading one. That means that this is n by n matrix with n leading one. Leading one. Sorry, n by n row reduced echelon form. Row reduced echelon form with n leading one is actually identity matrix, the identity. So that is what we have. So that means that row echelon form of A, reduced row echelon form of A is identity. Well, then from fourth one to the fifth one is now easy, because what does a row reduced echelon form of A being identity mean? It means that there's a sequence of row operation. If we apply on A, we get identity matrix, yes? So let me say I do the first elementary row operation on A, then this one you can write it as one elementary matrix multiplied to A. The second one of these operations, if you apply, you get E2 times E1A. Remember, all elementary row operations can be realized by matrix multiplication by an elementary matrix. So you do all these elementary row operations. Let's say k of them exist. So this means that we have ek up to e2 e1 times a equals, at the end we got identity matrix. Okay. Now these guys are invertible matrices. E1, all elementary row elementary matrices are invertible. So the product EIs are invertible. Then EK times E1 up to E1 is invertible. And that means that I can take this or multiply both sides by the inverse of EK up to E1, and we get A equals to EK up to E1 inverse. Well, if you have that thing, you know that product and invertibility, how that works. You have inverse of each one, but you order them in the opposite order. So E1 inverse up to EK inverse. Okay, so we wrote A as product of inverses of elementary matrices. But we know that inverse of elementary matrices is another elementary matrix. So let me just write it as E1 tilde, E2 tilde up to EK tilde, where EI tilde is EI inverse, which is another an elementary matrix. Very nice. So we proved the fifth one. How about from fifth one to the first one? This is now easy. So the fifth to the first one. If a matrix is product of the elementary matrices, since elementary matrices are invertible, their product is invertible, and hence A is invertible. So this completes the proof of the theorem. You have to know this different versions and you have to be able to use them. One of the very nice applications of this is that, well, if you have, let me just write as a corollary here. Let again A, B, and then by n matrix. If there is a B, if BA is equal to identity, then we can conclude that B is A inverse. Yes. What is important about this thing? Remember, the definition of invertible inverse is that not only when you multiply from left you get identity. So let me write this. Not only you multiply from left, but also you multiply from right, also you get identity. Here this says B, when you multiply to A from the left, or let's call it left inverse. If a B is left inverse, it will be the inverse. It means that you can conclude that AB is also equal to 0, and that will give you what you have there. Well, proof of this is very nice. This will use the third version. If AX equals to 0, we can multiply B there, so we get BAX equals to 0, and from there we get IX equals to 0. That means that X is equal to 0. That means that what? 0 is the only solution of AX equal to 0. Check the third one. The third statement says that, well, if that is true, then A is invertible. And if A is invertible and we have BA equal to identity, we can multiply both sides by A inverse from the right. So you will get BA A inverse equals to A inverse. This, you take these two together, this will give us identity equals to identity times A inverse is A inverse. Again, another time, identity times B is B. B is equal to A inverse. That's what we proved. And then the similar story goes, if you have AB equal to identity, you can show that it is the inverse. So right inverse is the inverse, left inverse is the inverse. Here we have to note that both of ABs need to be square matrices. Okay, this was fundamental theorem of invertible matrices. You have to know the different versions and different implications of these theorems.